Hello, my name is Galina Filipuk and I work for the University of Warsaw in Poland at the Faculty of Mathematics, Informatics and Mechanics. This presentation is done jointly with Dr. Andrzej Kozłowski from the same faculty. During my presentation, I will be discussing some aspects of teaching analysis with Mathematica and share our experience. We think that this might be interesting to people from other universities who already have or plan to create similar courses. Right now, especially in our current pandemic situation, many universities revise their courses, consider how to include more computations in any computer algebra system in their courses, and so our observations might be helpful. Although there are a lot of free resources, examples, recordings on the internet, for instance, at Wolfram U, but still not everything can be adapted for a concrete university syllabus, and a lot should be done from scratch. First, let me very briefly describe what kind of courses we teach. We have been given tutorials for the course of analysis for computer science students and for mathematics students for several years. And augmented is the standard course of analysis with computations in Mathematica, especially for computer science students. Moreover, we have written a two-volume book entitled Analysis with Mathematica, published by De Gruyter. The first volume appeared last year, and the second volume is to appear by the end of this year and can be pre-ordered on Amazon or publisher's website. So you will see the links at the end of the presentation. The book is with a lot of examples based on our experience, and it contains the necessary theoretical knowledge. And those examples are in turn taken from our faculty lecture notes. So we actually included some of the examples from these books into this presentation. A typical mathematics course at the University of Warsaw consists of lectures at which the theory is taught and of accompanying problem classes or tutorials. At the University of Warsaw, students who enroll into analysis courses, which are separate actually for mathematics and computer science students, are divided into groups of about 20 students each for tutorials. The course of analysis for computer science students lasts for 1 year, while for mathematics students, the course lasts for 2 years. The course for computer science students is, of course, easier, but it's more than the standard calculus course, and students are required to prove statements and to solve non-standard exercises. In general, students can use any recommended book on real analysis or lecture notes, and are only required to know the basics of the Wolfram programming language. Although we have an online course dedicated to learning the Wolfram programming language, it's not necessary to take it before enrolling into the analysis course. After taking the analysis course, students might choose a differential geometry course about curves and surfaces, which is also done with Mathematica. Many mathematics students enroll into this course. There are also some more advanced and specialized courses like differential equations with applications and elliptic functions, which are done with some use of Mathematica. One observation that we have noticed is that the computer science students, in comparison with mathematics students, learn the Wolfram programming language very fast, and they are more eager to experiment. Programming in Mathematica is easier for computer science students, but more difficult for mathematics students. So we try to choose problems for our classes in which Mathematica could be genuinely useful. This means that students do not only apply some standard algorithm or plot a graph, but they are required to think and to come up with some mathematical idea. Sometimes this idea is a guess inspired by mathematical calculation or a visual representation of the problems. Sometimes Mathematica can only verify this guess in special cases, and sometimes it can prove its correctness in full generality. In all such cases, we normally still want to obtain a rigorous mathematical proof. When using a computer program as an aid in mathematics, it's very important to understand what such programs are well suited to and what they are not, and also what kind of problems, including incorrect answers, one can run into. One more observation is that computer science students often rely on Mathematica and have difficulty in interpreting the results. I would like to mention that due to the current pandemic situation, almost all teaching in many countries has gone online, also in the coming winter term. Many people think what the future of education will look like. Mathematica combined with video conferencing software such as Google Meet, Zoom, Skype, or any other, which allows to share the screen, is a perfect replacement for the blackboard. It can be used in both online and blended learning modes. When we teach online or in class, we can write, show pictures, and give more educational material, for instance, demonstrations in Mathematica to students, which is very convenient. The students can see the screen of the lecturer and also experiment later on their own. Another observation that we have is that now students seem to be much more interested in using Mathematica, maybe due to the fact that it's more difficult to meet and study in small groups and in person. And so students are more eager to experiment on their own. In this presentation, we will present some examples of analysis of problems taken from our books, where Mathematica can be used effectively as an aid in solving mathematical problems, or at least inspire the idea of a solution. We believe that skills, say computational thinking acquired during the course of analysis, can be applied to solving more complicated mathematical or research problems later on. So let us have a look at examples. I shall present them from a very kind of didactic and pedagogical point of view. Maybe those examples are very elementary for experts in Mathematica, but we hope that they will be interesting to educators. So the first example that we have is about inverse of function of the hyperbolic sign. The reason why we chose this example is that we want to show how students would be required to think and learn about inverse functions. This example also demonstrates clearly why we should not always rely on Mathematica's output, and we shall show how we can verify the answer. Let us consider the hyperbolic trigonometric functions, which are in Mathematica are of course defined and built in as sinh and cos. Since in this example we do not want to use Mathematica's built-in knowledge about these functions, let us pretend that we ask students to define their own functions. So this step is usually done very quickly. Many students might then naively try to use the built-in inverse function. So unfortunately, in this example, the inverse function doesn't work correctly. In Mathematica 12.1, it chooses incorrect branch of the function. It can clearly be seen that this function doesn't take real values. At this step, we observe that many students might continue to work with this incorrect answer further and without paying attention to the message. Just as a remark for Mathematica developers, it's a pity that this version of Mathematica doesn't allow to specify the domain over which inverse function should be considered. Next, when we draw attention of the students to this problem of the incorrect branch of the function, we would normally ask them to obtain the correct answer and verify it. We might ask whether the function is invertible and then compute the derivative of its inverse. To show that the function sinh is invertible, we need to show that the equation sinh of x is equal to y has at most one solution. In fact, we will show that it has exactly one solution for every real y. This equation can be easily solved by hand, just using the substitution exponential of x is equal to t, and solving the resulting quadratic equation. So at this step, the students will verify both in mathematics and by hand that everything agrees. This means that the inverse function of sinh is correct, and we can now find its derivative directly. We would then normally reflect and think how we can improve our reasoning. We notice that the weakness of this approach is that it requires explicitly solving the equation f of x is equal to y for x. In general, this can be very hard and or maybe sometimes even impossible to do in explicit form. However, we do not need to solve the equation to prove the existence of an inverse function or even to find a formula for it. Since the function is defined in an interval, we only need to show that it is strictly monotone. We note also that the image of sinh is the whole real line. So since the derivative is positive everywhere, the function sinh has an inverse function defined on the whole R. We can now find the derivative using the well-known formula. Since the derivative of sinh is clearly cos, so this can be written as follows, just the last formula on this slide. This is indeed the solution of the problem, but it's not given in a very convenient form. So we can make use of the easily proved identity, and since cos takes only positive values, so we can take the positive square root. So finally, spending quite a lot of time on this illustrative example will allow students to verify everything by differentiating the Mathematica's building a function arcsinh. So students learn a lot of theory along the way and learn how to interpret and verify the computations. Another example is from the theory of functions of many variables. At the beginning, the students learn the properties of the Euclidean space Rn, and suppose that they are asked to determine whether the following set is bounded or not. This looks a little bit scary, and so students will normally try to use computer first. They're usually very happy once they discover the easy answer without it. So let us go through this example. Note that since there is no restriction on the variable z, the set is unbounded unless it is empty. So we need to find just one solution to prove that it is not empty. We can use the built-in function of find instance. Find instance found a rather complicated route, but that is all we need if we use a computer. Asking the students to guess a simpler solution and possibly given some more hints, we can actually find the following solution. So we draw attention of students to the fact that we need first carefully think about the problem and try to analyze it without a computer. And the next example is to find the local extrema of the function of three variables. The computations by hand are standard but quite long and tedious, and we think that doing such an example on a computer step by step helps remembering the necessary steps that should be done to get a solution. We remark that during exams at our university, the students are not allowed to use Mathematica. So learning the algorithm in this way will help them solve a similar problem by hand. First, we find the critical points. We next compute the Hessian matrices. We can compute the eigenvalues of these Hessian matrices by means of the function eigenvalues, but Mathematica has the function positive definite matrix Q, which makes everything even simpler. This tells us that the second and the third points are local maxima, but the case has to be decided separately. Let us have a look at the eigenvalues. There are one positive and two negative eigenvalues, so the critical point is neither local minimum nor local maximum. We could also have checked this by using the function indefinite matrix Q. So solving such algorithmic problems with computer has advantages as well. So I hope that my discussion today on some pedagogical aspects of teaching analysis with Mathematica will be very useful for educators. This approach develops computational thinking in students, and I personally think that it is very important. If you would like to see some more examples from analysis with Mathematica books and possibly use them in your courses, please consult those, please see those web pages. The links for the two volumes are given in this presentation. I thank you very much for your attention. Hello, are there any questions? I'm just interested to know if you work at the university, whether anyone has some experience in having kind of analysis or any other subject classes with Mathematica. Maybe you'll have to unmute your microphone because I don't hear anyone. Oh, I'm just addressing anyone. Okay, I'm looking at the chat right now. Did you use MMA online for online courses? Well, actually, we haven't done yet so, but since the next term would be online, so probably we would have to use some elements of this in our online courses next terms. So what about teaching analysis at other universities? Anyone tried to use Mathematica with teaching analysis? Okay, I have from the chat, I have taught mathematical analysis using Python. I've not yet taught using Mathematica. I don't know. So, So the way we use it is just we have so our local lecture notes with a lot of examples, and we try to use Mathematica just in those examples where we can use. Of course, if some problem is theoretical, then we will not be able to use Mathematica. But this is trying to go beyond just plotting the graph or showing some I don't know plot or just some simple computation. So we try to make people think about this. So I'm just not sure why I do not hear anyone because I can read the chat, but I don't hear anyone. Yeah.
Looks like Craig has a question.
Hello?
Hey guys, can you hear me?
Yeah. Yes, I can hear you.
My name is Vitaly Kourov, and yeah, hey, we already chatted a little bit. Galina, very nice talk. Thank you so much. I have a question. Maybe I have missed it because my connection was a little bit shaky. For how long you already teaching this course in Warsaw?
So this depends on my teaching load. So we started to teach this a long time ago, but it's not kind of year. So we have been developing this for a couple of years, but not consecutively.
I see. So, but you say a long time ago, on and off, but you mean like what, 1 year or 5?
Oh, no, it's like maybe 5 or 6 years. We tried once to organize some kind of an event in Warsaw with a Polish company, Gambit, kind of to promote this Mathematica. So this Gambit is a local distributor. So trying to promote kind of Mathematica and everything, but yeah, so somehow everything a little bit faded after that.
I see. And is the course itself lasts like a semester, like half academic year or something like that? I don't know, or it's longer.
Well, it depends on the course. So if we're speaking about differential geometry, then it lasts like half a year. If we're speaking about mathematical analysis for students, so this might be, if students for informatics, then it is 1 year courses. If we're speaking about mathematics students, then it is a 2-year course. If we speak about internet course, kind of on basics of mathematics, then it is again half year, but it's repeated sometimes even twice a year. So it really depends.
Okay. Got it. All right. I'll let other people ask questions. Don't want to take all the time. Thank you so much, Galina.
Thank you. Are there any other questions or maybe remarks? Because I'm really kind of curious how other people use Mathematica in online, in general, in teaching, either online or face-to-face. So I just don't see any comments or raised hands.
Galina, you mentioned that this was for computer science students.
Yeah.
How did you find, oftentimes computer science students aren't necessarily the top Mathematica, or excuse me, mathematics, students that comprehend mathematics well. How did you find that your course has benefited computer science students in learning and understanding maths more?
So thank you very much for this question. Actually, it's a very interesting observation that we had. So if we teach Mathematica for computer science students, then computer science students learn just programming language and everything very quickly, but they have difficulty in interpreting the results, like mathematicians. If we, on the other way around, if we teach mathematics students and try to give them the basics of mathematical language and everything, but they're a little bit not so quick with maybe learning it, but they are better in understanding how to interpret some results and how to do a little bit more steps. So if, for instance, suppose that the problem requires first one step doing something in Mathematica, maybe plotting or something, then a little bit thinking, then doing something else. So in this kind of many step solution, mathematics students seem to be a little bit better, and interpretation for computer science students is a little bit worse. And also, so computer science students have their program, and actually we have like extra classes for them. So first they just to go through this set program curriculum for them. And in general, it's only, so this course is kind of optional for them. Some part of computer science students just learn mathematics according to curriculum, and some students join our class and they have additional time to learn Mathematica and to use it in doing the problems as the rest of the students, if this helps. So this is the way how it works at the University of Warsaw.
So did the course include both computer science and mathematics students in the same course? You paired them up so that the computer science students gained from mathematics students comprehension, and mathematics students gained from the computer science students' ability to code and you know.
No. They mathematics and computer science students have different curricula, and they are never mixed in or classes.
Okay, thank you.
So,
Galina.
yeah, thank you.
Galina, so I might have missed it again. Have you ever tried to sort of repackage this course and share it with another academic institutions? Is it, if not, if it's repackageable in general, are materials shareable? Do you have curriculum developed and lesson plans, something like that?
So the voice was not very clear, but I think maybe I missed some part of the question. But if I understood correctly, you're asking about how whether I tried to whether our course is kind of transformable to other universities. Is that correct? Yeah.
Yes, absolutely.
Yeah. So actually, we have written a book because so this is the book, which two-volume book with just 6 chapters in one, and was it 5 or 6 chapters in the other one. So, and it goes just along the usual course of analysis, say starting with sets, then sequences, series, well, I don't know, functions of 1 variables, functions of 2 variables, minima, maxima, and so on and so forth. So the only kind of with everything that we teach some theoretical material, and we explain how to do some examples in Mathematica and how we to try to do this. So we never tried to get in contact into some with some other university, but actually our book is just for well, just in attempt to reach out a little bit outside of our university and try to show what we are doing, and maybe some other people from other universities would be interested. In general, I'm interested in kind of this, in general, developing maybe either curricula or something for like teaching analysis and some courses, but maybe one of the problems is that at each university, everyone has its own curriculum. So on the one hand, the book is kind of transferable, so anyone can take it and use it, use the chapters. But on the other hand, we haven't yet tried to reach out to some particular university and try to do the course for them. But it would be a very interesting experience, of course.
So I think like a book is a great general idea. It's awesome that you guys wrote it. I am also just curious, you know, for example, by the way, until I forgot, so you were curious about other experiences. So for example, Wood from you, this is like Wood from academic institution, has sort of, not, I wouldn't say similar, but we have a course which is called Introduction to Calculus, and it's packaged as a MOOC. So people basically can go through the chapters, review videos, and go consistently through the topics. It was developed by one of our internal great mathematicians, Devendra. So you can take a look at that course. It's free online. I'm not sure if you've seen it already, maybe.
Yeah. So I had a look at them, but the problem is that some of the examples or problems are a little bit too elementary for our students.
Yeah, I understand that. I was just trying.
For mathematics students, it's not very much suitable. So it's more question how you use Mathematica for educating, like analysis, not the calculus, but kind of analysis where you need a little bit more kind of to think.